In this video, we will practice the 5 different rules there are for evaluating or simplifying exponents. So the first rule is when you are multiplying like bases, you add the powers together. So if I had a base of 5 and a power of 2, and I was multiplying that by another base of 5 to the power of 5, then I would keep this base the same, and I would add these two exponents together. So 5 to the second power times 5 to the fifth power is 5 to the seventh power. If I had 4 to the eighth power times 4 to the sixth power, I would get 4 to the 14th power. This can work with any type of powers, even negative powers. If I had 3 to the 7th power and I multiplied it by 3 to the negative 10th power, I would get an answer of 3 to the negative 3rd power. This rule of adding the exponents only works if the bases are alike. So if I had a problem like 5 to the 3rd times 3 to the 5th, I could not simplify it into one single base and power. I would have to evaluate 5 times 5 times 5. I would have to evaluate 3 times 3 times 3 times 3 times 3, and then I would times these two products together. Multiplying like bases means you leave the base the same and add the exponents together. Let's take a look at the next rule. Dividing like bases. If you have two bases that are alike and you are dividing them, you can subtract the powers. So if I had 5 to the 7th divided by 5 to the 3rd, I would leave the base of 5 the same and subtract, starting from the numerator, 7 minus 3. If I had 3 to the 8th divided by 3 to the 4th, I would keep the base the same and subtract, not divide, subtract the powers. This would work with negative powers too. If I had 2 to the 7th power divided by 2 to the negative 3rd power, I would leave the base the same and I would subtract the exponents. But look what happens if I did 7 minus a negative 3. You see what we have here? This combination means I add the opposite sign. So I would actually get 2 to the 10th power. W to the 9th divided by W to the 7th would be W to the 2nd. When you are dividing like bases, you leave the base the same and subtract the exponents. Now let's take a look at the final rule. Raising a power to a power. If I have a base that already has an exponent, and I'm going to raise it to another exponent, I'm actually going to multiply the powers together. So if I had 3 to the 5th, and I'm going to raise that to the second power, I'm going to get 3 to the 10th. Because technically, I want 3 times 3 times 3 times 3 times 3, or 3 to the 5th, and I want to have that 2 times, right? I want to square that. So I would be multiplying that again by itself. 3 times 3 times 3 times 3 times 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. there are 10 bases of 3. And that's why I get that power. Another way to think of it, if I have 5 to the 7th power and I want to raise that to the 3rd power, is to think about the fact that this power is touching the parentheses. And anytime you have a value that touches parentheses, like let's say something like this, anytime you have a value touching parentheses, it is implied multiplication. So you would distribute or multiply there. So 5 to the 7th power, raised to the 3rd power, leave the base the same, and multiply the powers. Four to the 5th power, raised to the 6th power, is 4 to the 30th power. Now be careful to look at your bases when you have an expression raised to a power. If I have, let's say, 5m to the 5th power, and I'm going to raise that entire expression to the 3rd power, then look carefully what I do. I'm going to multiply this exponent times this exponent. But 5 and m are actually two separate factors. That's 5 times m to the 5th. So that means 5 has his own invisible power. So that means I would distribute this power to 5 as well. So if I have 5m to the 5th power raised to the 3rd power, I actually will get 5 to the 3rd power and m to the 15th power. They both would be multiplied by themselves 3 times, right? So 5m to the 5th times 5m to the 5th times 5m to the 5th. And now you can clearly see that there are 3 5s. The last 2 rules are rules that you need to know for when your answer gets one of these types of powers. So it's not an operational rule, but it's what you do when your answer looks like one of these numbers. So earlier, I gave you an example kind of like this, where I had 3 to the 5th times 3 to the negative 7th. And I got an answer of 3 to the negative 2 power. So sometimes, when you're done simplifying using your power rules, you actually get a negative exponent. So let's think about this for a second. If I have 3 times 3 times 3 divided by 3 times 3, let me add another one up here. If I had this, and I wanted to simplify it, then couldn't I say that this creates one whole, and this creates one whole? 3 over 3 is the same as 1 over 1, and 3 over 3 is the same as 1 over 1. So that means my answer would be 3 squared, because I have 2 3's left over. Now what if I had this expression? 3 times 3 divided by 3 times 3 times 3 times 3. Can't I use those same practices? 3 divided by 3 is 1 whole. 3 divided by 3 is 1 whole. And I have 2 3's left over. But if I said that the answer to this was 3 squared, and the answer to this was 3 squared, how could that be possible? If this has 2 3's left over in the numerator, and this one had 2 3's left over in the denominator, that's clearly not the same location, so they can't have the same answers. So the rule is, if you have bases left over, but they're down here in the denominator, then they cannot be equal to 3 to the positive 2 power. These 2 3's reduce to 1. So technically, my answer is I have two threes left over, but I have them down in the denominator. And over here, I had two threes left over, but I had them left over up in the numerator. Do you see the difference? If I don't want to write my answer as a fraction, if I don't want to write my answer as a fraction, I can simply take my base and my power and move them up to the numerator, but I have to indicate that I'm moving them. So when I do that, I write the power as a negative. So 3 to the negative 2 power means I have two threes left over, but I have them down below in the denominator. You see that? That negative sign indicates that these two threes that I have are really down below here. So if I had something like this, 5 to the second power, that means that I have two 5s in the numerator. But if I have 5 to the negative 2 power, that means I have two 5s in the denominator. And the denominator cannot have an invisible numerator. So I would fill in my 1 there. And I could simplify that to this. So if I want to take my negative exponent and turn it into a positive exponent, I have to put the base back where it belongs, down here in the denominator. But once I move it, do you notice the negative sign goes away? So if I have 3 to the negative 5th power, that means I have 5 3s, but they're supposed to be down in the denominator. So I move my 3 down to the denominator, and my power becomes positive. But I have to fill in my invisible placeholder numerator. So anything with a negative power is just in the wrong location. So I have two 7s, but I don't have them up here in the numerator. I have them down here in the denominator. When you take the reciprocal, the power becomes positive. So the rules for negative exponents state that you take the reciprocal of the base, 1 over a, because technically this is a over 1, and you make the power positive. So if I have 7 to the negative 8th power, I take the reciprocal of 7, which is 1/7, and I make the power positive. Now if I have a power of 0, let's say I have 5 to the 3rd, and I want to divide that by 5 to the 3rd. That means I have 3 5s in the numerator and 3 5s in the denominator. And whenever your numerator and denominator match, they reduce to what? They don't reduce to 0. 5 over 5 reduces to 1 over 1, right? 5 over 5 reduces to 1 over 1. 5 over 5 reduces to 1 over 1. And what's 1 times 1 times 1? It's 1. Let's take another look at that. If I have 3 to the second divided by 3 to the second, then I have two 3's in the numerator, two 3's in the denominator, and I have two wholes, right? 3 divided by 3 is 1, 3 divided by 3 is 1, but 1 times 1 is actually just 1. Now if I apply my rule from earlier, which is that if my numerator has a base that matches my denominator that has the same base, I can subtract the powers. Well, what's 15 take away 15? It's 0. But just like I showed you in my smaller example, when you have the same powers, you have the same amount of pairs, and they will always reduce to 1. So anything that has a 0 power can be reduced to the number 1 because you have whole matches here. So these last two rules here, negative exponents and 0 exponents, are rules you may need to use when simplifying a longer math problem. So let's take a look at some questions and see how you do. Pause the video and try some of these true or false questions and see if you can get them right. Okay, unpause the video now and let's take a look. When you have like bases and you are multiplying, you add the powers together. You add the powers together. So the answer here should be 9 to the 7th. So that's false. When you raise a power to a power, you multiply the powers. So this one is true. Now here, these are not like bases, but I can distribute an exponent throughout my factors. So this one is true. This has an invisible power of 1. This one has an invisible power of 1. So 2 to the 6th times 4 to the 6th. Now there's no shortcut for this though. You cannot simplify this and get 8 to the 12th. You cannot do that. Alright, anything raised to the 0 power means that we have an exact match in the numerator and an exact match in the denominator, so they cancel out to wholes. Not zeros, to wholes. So the answer to that was 1, so that's false. When you divide like bases, you subtract. You don't divide. You subtract. So that one was false. And anytime you have a negative power, that means that your base is in the wrong location, right? So 3 to the negative 2 power means take the reciprocal of 3 and make the power positive. So 1 over 3 squared. And 3 squared is the same as 9, so that's true. Alright, pause the video if you haven't tried the next 5. Is each expression equivalent to 16? So when I divide like bases, I subtract powers. And yes, 4 squared is 16. Anything raised to the 0 power is 1, not itself, 1. So that's not a 16 anymore. 2 to the 1st times 2 to the 3rd is 2 to the 4th. So 2 to the 4th is 2 times 2, which is 4, times another 2, which is 8, times another 2, which is 16. So that's a yes. 2 times 2 to the 2nd, well, I can distribute this here, and I would get 2 squared times 2 squared, right? Keep the base, add the powers, and I would get 2 to the 4th. And we just did 2 to the 4th right here, so the answer is yes. 8 to the 2nd power, that's 8 times 8, not 8 times 2. 8 times 8. So the answer is no. Hopefully that helps you to understand the 5 rules of exponents.